Welcome back to the AI Research Roundup. I am Alex. Alright, today we're diving into a really interesting paper from the Papers with Code trending list, published May 16th, 2025. It's called Visual Planning. Let's think only with images. So the main idea is that relying purely on text for AI reasoning isn't always ideal, especially for tasks needing spatial awareness. This paper introduces visual planning, where planning happens through sequences of images, kind of like how we might visualize steps. They've developed a novel framework, visual planning via reinforcement learning, or VPRL, which uses a trial and error learning approach to significantly boost how well large vision models can plan in visual navigation scenarios. And it's great, they've also released the code for this work. So over on GitHub, you'll primarily find the evaluation scripts and assets to help reproduce their visual planning results. They also mention that modeled checkpoints, which are saved states of their trained AI model, and datasets should be coming in the near future. Alright, so to better understand what they mean by visual planning, let's look at Figure 1. This figure, it really clarifies the core idea by comparing different reasoning paradigms. The top and middle rows show traditional language-mediated approaches, like direct prompting or multimodal chain of thought. Here, the AI uses text, verbal thoughts, to plan, even with visual input. But the bottom row, that's the visual planning paradigm. With this approach, an initial image leads to a sequence of visual thoughts, essentially predicted future images forming the plan, entirely without intermediate text. The planning stays completely in the visual domain. So to actually make this visual planning happen, the paper introduces their framework, Visual Planning via Reinforcement Learning, or VPRL. This system uses what they call a large vision model, which, importantly, is trained only on images and video frames, no text at all. VPRL then learns in two main stages. First, there's a policy initialization phase, where it learns from random visual paths. And then, it refines its planning through reinforcement learning, guided by a special progress reward function to tell if it's making good visual steps toward the goal. Okay, Table 1 here really drives home the effectiveness of this visual planning via reinforcement learning approach. It shows performance across 3 different visual navigation tasks: frozen lake, maze, and mini behavior. We're looking at metrics like exact match, which is how often the model perfectly reaches the goal, and progress rate, which reflects how efficiently it makes good steps towards that goal. And you can see the visual planning via reinforcement learning model, noted as VPRL and using only images for both input and output, consistently outperforms other methods, including those relying on text, often by a significant margin. Alright, so Figure 3 gives us a more concrete look at these visual planning traces in action. We see examples from the same 3 tasks: frozen lake, maze, and mini behavior. For each task, the images show sequences representing different kinds of actions the model might plan, like an optimal action, which is the most direct path to the goal, a non-optimal one, which still works but takes a longer route, and an invalid action, such as trying to move through a wall in the maze or violating a physical constraint in mini behavior. This illustrates how the system visually thinks through possibilities. Okay, building on those visual traces, Figure 4 gives us a direct comparison in a frozen lake test. At the top, we see how language-based models tackle this. Gemini 2.5 Pro, for instance, uses text to reason, but incorrectly concludes no valid path exists. Another model, QN 2.5 VL, gives instructions that actually violate the game rules. Then, the middle row shows visual planning via fine-tuning, or VPFT, which is that initial policy training stage. It finds a path visually, but it's a non-optimal one. Finally, the bottom row shows the full visual planning via reinforcement learning, clearly navigating to the goal with an efficient visual plan. So, Figure 5 takes that frozen lake comparison a step further, specifically looking at how these different models handle increasing difficulty. The horizontal axis here represents the grid size, essentially how complex the frozen lake environment becomes, ranging from 3 by 3 up to 6 by 6. And the vertical axis shows accuracy. What's really telling is that as the grid gets bigger, the accuracy of the language-based models, like Gemini and Qwen, drops off quite sharply. But the visual planning methods, especially visual planning via reinforcement learning, maintain higher accuracy and show a much more gradual decline. This really demonstrates their greater robustness to increasing task complexity. Okay, so to understand a bit more about why visual planning via reinforcement learning might be more robust, Figure 6 here digs into the exploration capabilities during the initial learning phase, again on the frozen lake task. We're comparing visual planning via fine-tuning with the first stage of visual planning via reinforcement learning. The vertical axis shows average entropy, which, in this context, measures how diverse or varied the model's attempts are when it's trying to find a solution. The horizontal axis is the percentage of invalid actions. Notice how visual planning via reinforcement learning stage 1, that purple point, shows high entropy and a low invalid ratio, so it explores broadly yet efficiently. In contrast, visual planning via fine-tuning, the orange line, tends to explore less and make more invalid moves as its training progresses through more epochs. That superior exploration capability really underscores the strength of visual planning via reinforcement learning. This paper compellingly shows that enabling models to think directly with images, rather than relying solely on language, can lead to more robust and efficient solutions for complex visual reasoning challenges. It's a fascinating direction for AI. Well, that's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.